All right, we're back again for some more math. On the way over, though, to film the lessons today, I stopped at the bank, and there was this really nice old lady, and she asked me if I could check her balance. So I pushed her over. She fell. Just kidding, I would never do that. That's terrible. All right, we're going to start talking about absolute value, which in IM1 we talked a little bit about absolute value and specifically the graphs of linear absolute value equations. But first, just what is absolute value? Absolute value is the distance, and this is the key word. It's the distance from a point to zero. When we do absolute value, we use these bars. So we would read this as the absolute value of -4. And the absolute value of -4 is 4 because we're finding the distance that -4 is from 0. To go from -4 to 0, we have to go 1, 2, 3, 4 spots. So it's 4 spots away. The distance is 4. Likewise, if we're finding the absolute value of 5, we're finding how far away 5 is from 0. So 1, 2, 3, 4, 5. It is 5 spots from 0. The key with absolute value is we're talking about distance, and distance is always positive or 0. But when we talk about distance, we don't use negative numbers, right? We don't say, oh yeah, the mall is -3 miles away, or I'm going to go run a -2 mile run today, right? So distance is going to be positive, and that's why when we're finding the distance of a negative number, we use a positive, because the distance will be positive. As far as graphing absolute value, that's what we're going to focus on today. We know quadratics already. That's what we've been working on for quite some time. And we know the graph of a quadratic is a U-shape. Absolute value is actually fairly similar. Absolute value, you might remember from IM1, is going to be a V shape. It's similar to quadratic because it has a section that decreases and a section that increases. Like a quadratic, it'll either have a minimum or a maximum. And that minimum or maximum we will call a vertex, just like we did with quadratic. So if you understood vertex form of a quadratic, which is what we did last week, then understanding, or 2 weeks ago, understanding the formula for an absolute value graph, it's pretty much the same exact thing. So the biggest difference is in a quadratic we had parentheses squared, right? Squared indicates quadratic. In absolute value, instead of parentheses, we have the bars, right? And what do the bars mean? The bars mean absolute value. There's no squared because it's not a quadratic. And oftentimes, sometimes we actually do use A, H, and K for absolute value, but we're going to start to transition you a little bit into something called transformation form, which is where we use a capital A, a capital C, and a capital D. But it's the same exact thing. This A here and this A here are going to indicate, does your graph open up or down, and is it stretched or compressed? So this is still going to be up versus down, and stretch, compress. So the A value still does the same thing. The H in quadratic is the same thing as this C in the absolute value, and that's going to be your horizontal shift. Right? So I know if this said x minus 4, my graph would move 4 to the right. Same thing, if this said x minus 4, my graph would move 4 to the right. It's the same thing. And then the end of the equation, so the k in quadratic, or the plus d in absolute value, is our vertical shift. So it's going to tell us how much the graph is shifting up or down. And just like our vertex is opposite of H and then K, our vertex here is just going to be the opposite of C and D. So it's really the exact same thing. Okay, so if we're given these equations, absolute value equations, we can identify the vertex. We can also identify if it's a max or min based on whether it opens up or down. So absolute value, we know it's absolute value because of the bars, right? It's not quadratic, there's no squared. But our vertex is still the same process as before. It's the opposite of -5, which is +5, and then the value at the end is our y-coordinates. Our vertex is 5, 3. Because our A is positive, we know the graph will open up, so it's going to be V-shaped, right? Not a U-shape, it's going to be linear, so you have two straight pieces. But because it opens up, we have a vertex at the bottom, which means we have a minimum. So again, very similar to what we've been doing. Vertex here, it's going to be the opposite of 1, so -1, and then the number at the end, -9. What if there is no number at the end? Actually, we'll come back to that in a second, sorry. Because this is a negative A value, it's going to open down. The fact that it's a -3 means it's going to be stretched, so it's going to be a narrow graph. But because it opens down, our vertex is at the top, and we have a max. All right, back to this one. The vertex, we look inside of our bracket. That's going to be opposite of 2, so -2. And then what if there's no number at the end? That just means the graph is not shifted up or down, so our y-coordinate is 0. And then as far as opening up or down, we have a negative in front, so it's going to be an upside down V, right, or kind of like an A. And if it's upside down like this, our vertex is at the top, and we have a max. And then finally, vertex here. It's always the number that's inside the bars. And so since there's no number being added or subtracted in the bars, it means our x-coordinate is 0. There was no shift left or right. But our y-coordinate is going to be the number on the outside. So our vertex will be 0, 2. And then because we have a positive A, we know it's going to open up. And if it opens up, that means our vertex is a minimum. So again, very similar. Biggest differences are that we have a V shape instead of a U shape. And the actual equation has bars instead of parentheses with a squared. All right, graphing. We're going to actually expect you to graph these. The good news is they're very simple to graph. If we graph the parent function, first thing I'm going to find is the vertex. Well, there's nothing added or subtracted inside. There's nothing added or subtracted at the end, so our vertex is 0, 0. So I'm going to put a point at 0, 0. And then our A value is actually a slope. So just like when we did linear equations in IM1 and we drew straight lines, whatever our A value is going to indicate the slope that we use for 1/2 of our graph. So I know it's going to open up because my slope is positive. And if I go to my vertex, sorry, opens up, because slope is positive, right? A is positive. If I go to my vertex, I'm going to use a slope of +1. So I'm going to go up 1 over 1, up 1 over 1. Continue to do that. But we need a V shape. So from the vertex, I'm going to make the vertex a different color just so we know that that's a key point, right? That's the place where we're going to change direction. So if this side of the graph is going up 1 over 1, that means that the other half of the graph is going to do kind of the opposite. We're going to go, instead of up 1, right 1, we're going to go up 1, left 1, up 1, left 1. And so we end up creating a mirror image. And the slope of this half is technically -1 because it's decreasing. But we knew it had to open up, right? So we have to be going up. And to get each new point, we go up 1 over 1, up 1 over 1. Similar to a quadratic, we have an axis of symmetry, right? Our line of symmetry would be x equals 0. We have an interval that's decreasing and then an interval that's increasing, so we still have those types of questions we could ask. We still have a domain of all real numbers. We have a range of y is greater than or equal to 0, just like we did with quadratics. Okay, this next one, the vertex is going to be 0, 0 again, because we don't have anything in the bars, and we don't have anything at the end. But what's different now is the slope is 3. It is a +3, so we know our graph's going to open up. I'm going to put my point on my vertex because that's our key point where we're going to change direction. But now instead of counting up 1 over 1, up 1 over 1, how much do you think we're going to count up before we go over? Well, our slope is 3, which is the same as 3 over 1. So from my vertex, I'm going to count up 3 over 1. Up 3, I got to go a little bit off the graph, over 1. And so that side of the graph looks like that. And then the other side of the graph, we know it needs to be a mirror image. So I'm going to go up 3, but backwards 1, up 3, backwards 1. And we get a nice V shape, right? No curves. This one is skinnier than this one, right? It's more stretched, and it's more stretched because we now have a slope of 3 instead of 1. So it's going to make it dilate by a factor of 3, making it skinnier. Okay, our vertex, opposite of negative 4, so positive 4, and then the y value at the end, 4, 2. I'm going to put 4, 2 on the graph. That's our critical point. Our slope is going to be negative, so negative 1. And because it's a negative, we know the graph will open down. So I'm going to go to my point, and I'm going to count down 1 over 1 because it's a negative slope. I could go down 1 over 1 again, right? And I can put as many points as my graph will allow. So then how do I get the other half of the graph? Well, I need it to be a mirror image, so I'm going to go down 1, backwards 1, down 1, backwards 1. And we can keep doing that all the way down. And we get a nice V-shaped graph, right? We could extend that if we had more graph to use. But we know it has to open down because our A value is negative. And we know because it's negative 1, every time we go down 1, we go over 1. All right. Next example, vertex will be negative 1, negative 3. We know our slope is positive 2. And then because it's a positive, we know it's going to open up. So I'm going to put my vertex at negative 1, negative 3. And then from there, how am I going to get more points? Well, I'm going to use my slope of 2 to count up 2 over 1, up 2 over 1. And that will give me the right side of my graph. And to get the left half of the graph, I just do the opposite. Up 2, backwards 1, up 2, backwards 1. And we end up getting a nice, perfectly symmetric V-shaped graph. All right, without using Desmos or without using a coordinate plane, we could write an equation and then identify lots of characteristics. So I know it's absolute value, so I need to have my bars. If my A value is 2, that means my number out front is 2. If my C is positive 4, that means in here it's going to say x minus 4. And then if our D value is 10, that means it's going to say plus 10. What are some things that we know about this graph? Well, we know the vertex. What is the vertex? Positive 4, positive 10. We know which direction it opens. If this is positive, our graph will open up. If our graph opens up, that means our vertex will be at the bottom, which means the vertex is a minimum. Then we could actually come up with quite a bit more. We know that the line of symmetry will go through the vertex, so our line of symmetry would be x equals 4. We know that because it opens up, our range would be y is greater than or equal to this y coordinate, so y is greater than or equal to 10. We would know that the interval of decrease would be from negative infinity until the x, which is 4, and then the interval of increase would be 4 to infinity. So we actually know quite a bit. We know the domain would be all real numbers. The second one, I'm going to do f of x. My A value is negative 1, so that means in front of the bar I'm going to put negative. I could put -1, but I don't really need to, right? Because negative implies -1. If my c is -3, then this will say x plus 3. And then if our d value is -5, it'll say -5. So again, 3 of the more important characteristics that we could identify. One would be our vertex, which is going to be opposite of this, so -3, -5. We know because the a is negative, our graph will open down. Because our graph opens down, we know our vertex is a maximum. And then we could go find things about our axis of symmetry, domain, range, intervals of increase and decrease. But these are the key points, the key pieces of information. All right, so we're going to write a few equations compared to the parent function. So the parent function would just be f of x equals the absolute value of x. So we're going to change that equation to make it do these different transformations. So first, if I want it to reflect over the x-axis, the only thing that needs to change is that instead of a positive absolute value of x, we need a negative absolute value of x. That'll flip your graph upside down. If we want the graph to stretch by a factor of 4, where do we need to put the 4? The 4 needs to go in front of the absolute value of x. So we know that graph would open up, but it's going to be stretched by a factor of 4. Translation 5 right and 7 down. Well, if I want to go 5 to the right, that means my x coordinate would be +5, which means this needs to say -5. And then to go 7 units down, -7. So again, hopefully this is pretty simple for you because it's the same thing we did with quadratics. Vertical stretch by a factor of 4. Hey, we already did that. My bad. But we'll go ahead and move on to this one. Reflection over the x-axis. So how do we make it reflect? We make it negative. Dilated by 1/2. So that's going to end up being a compression. The graph will be wider because that's between 0 and 1. Translated 2 to the right. Well, if I'm going to go right, I need it to say negative in my bars. So x minus 2. And if I want it to go up 15, we need plus 15. So again, writing the equation, it's basically the same thing as vertex form for a quadratic. That's basically the same formula we use for absolute value, just with bars instead of parentheses squared. All right, I'm going to skip this. It's a little too small to read. But as a way to summarize some of the key information, if we add the d value, or kind of like the k in vertex form, if we add a number at the end, if that number is less than 0, such as if we have f of x equals absolute value of x minus 5, where will that graph shift? It'll shift down. But if our d value is bigger than 0, such as f of x equals absolute value of x plus 5, the whole graph will shift up. Right? So that value at the end moves our graph up or down. Doesn't flip it, it just moves the whole thing up or moves the whole thing down. The a value out front, right? If that a value is less than 0, so if we have a negative number, so f of x equals negative, I'm just going to put a negative. That will reflect it. If our a value is between 0 and 1, so let's say it's 1/2 absolute value of x, will that stretch it or compress it? Well, because it's 1/2, that means instead of going up 1 over 1, we're going to go up 1 over 2, which is going to make our whole graph wider. So this will make it compressed. But if our a value is bigger than 1, such as if we have 5 times the absolute value of x, instead of going up 1 over 1, we're going to go up 5 over 1, which is going to make it much skinnier, narrower, or stretched. And then finally, inside the brackets, the C value, or kind of like our H value, if C is less than 0, so if C is a negative number, it'll actually turn into a positive in the bracket, so something like x plus 4. Because if we plug in a negative 4, negative 4 would turn it to plus 4. And that will move our whole graph left, so shifts left. But if we plug in a number bigger than 0, such as 5, and we get f of x equals x minus 5, that will shift our whole graph to the right. So same thing we were doing with quadratics. All right, so just to kind of summarize at the end here, absolute value and quadratics, their graphs are very similar. They have a lot of things in common. Some of the things they have in common, they have a vertex, they have a max or a min. They're gonna open up or down. They will always increase and decrease. All right, one half of the graph is going to go up, the other half of the graph is going to go down. Domain is all real numbers. All right, so there's quite a few things that they have in common that are very important. But there's a couple things that are very different. So absolute value is going to be bars, right? Absolute value bars. Whereas quadratic is going to be squared, right? So quadratic is squared, absolute value is bars. And then the biggest difference is the graph of absolute value will be V-shaped. So V-shaped. Or we can flip it upside down, where a quadratic will be U-shaped. It's going to have curves. The slope of this graph is changing. No matter where you are on the graph, it's going to be a different slope than other places, whereas this one's going to maintain the same slope throughout the graph. But because they have so many similarities, and our transformation form of absolute value is basically vertex form from quadratics, this should be a pretty easy lesson to understand, hopefully. Anyway, that's it for today. Hope you guys are doing great. If you have questions, make sure you're reaching out to your teacher, and we will see you tomorrow.
Bye-bye.